The universe begins in darkness, and in that darkness, it begins to breathe. Close your eyes and let your mind drift outward, past the walls of this room, past the sky above you, past the moon and the sun and every star you have ever named. Let it drift further still, into the vast and silent ocean of space, where distance loses its meaning and time moves so slowly that it seems to stop entirely. Tonight, we are going to travel there together, softly, without hurry, and ask a question that has occupied the quietest corners of human wonder for as long as we have looked up at the night sky. What if black holes connected every galaxy? What if these strange, invisible giants, the ones we imagine as points of destruction, were actually threads holding the universe together? But before we can answer that question, we need to understand the scale of the stage on which this story unfolds. So let your breathing slow, let your body sink into stillness, and let us begin at the very edges of what we can know. There are hundreds of billions of galaxies scattered across the observable universe. Not hundreds, not thousands, hundreds of billions. Each one of these galaxies is a city of stars, some containing a few 100 million suns, others containing many trillions. Our own galaxy, the Milky Way, is one modest neighborhood among this uncountable multitude, home to perhaps 200 billion stars, and yet it is only a single grain of sand on a beach that stretches beyond comprehension. Picture standing on a shoreline at night, looking out over dark water, and realizing that every single grain of sand beneath your feet, every one you could ever count in a lifetime, represents just one galaxy. It is a number the mind cannot truly hold, only gesture toward, the way we gesture toward eternity or the way we gesture toward sleep, knowing we cannot observe the moment we cross into it, only that we will. And these galaxies do not sit close together. They are separated by enormous distances, distances so vast that light itself, moving at the fastest speed anything can move, takes millions or even billions of years to cross the space between them. The nearest large galaxy to our own, a great spiral we call Andromeda, is over 2 million light-years away. That means the light entering your mind's eye right now, if you were looking at Andromeda through a telescope, left that galaxy before humans existed. It has been traveling through the dark, patiently, silently, for 2 million years, just to reach this quiet moment. Space, on the scale of galaxies, is not just big. It is almost entirely empty, a vast dark sea with tiny scattered islands of light. And yet, despite this loneliness, despite this seeming isolation, galaxies are not adrift at random. They are part of even larger structures, gathered together the way stars gather into galaxies, and the way galaxies themselves gather into something greater. Our Milky Way belongs to a small cluster of galaxies we call the local group, and the local group belongs to something even larger, a vast structure called the Virgo supercluster. And even that supercluster is just a strand within something more immense still, an enormous cosmic web that stretches across the entire observable universe, connecting galaxies into a structure that resembles, in shape, something almost organic. If you were to zoom far enough out, past every star, past every galaxy, and view the universe as a single object, you would see something that looks remarkably like a web of neurons or a network of roots beneath a forest floor, glowing softly with light, thin filaments crossing vast darkness. Within this cosmic web are galaxy clusters, and these clusters contain hundreds or even thousands of galaxies, all bound together by gravity, all slowly orbiting a shared center of mass. Imagine a great slow dance, choreographed not by any conductor, but by the patient pull of gravity across millions of years, galaxies drifting and turning around one another in an arrangement too vast and too slow for any living eye to witness in a single lifetime. If you watched a galaxy cluster for 100 years, you would see nothing move at all. And yet it is moving, always moving, drawn together in an embrace that will not complete for eons. Between these clusters lie the true emptiness of the universe. And the universe contains gigantic cosmic voids, regions of space so devoid of galaxies that they stretch for hundreds of millions of light years with almost nothing inside them. These voids are some of the largest structures we know of, vast bubbles of near-total emptiness, bordered by the glowing filaments of galaxies that outline their edges. If the galaxies and their clusters are like cities and towns, the voids are like the vast wilderness between them, silent, dark, and largely untouched. And yet even here, in what seems like true emptiness, something faint persists. Because space between galaxies isn't completely empty. It contains a thin, scattered gas, stray atoms of hydrogen and helium left over from the earliest moments of the universe, along with faint traces of dust and the whisper of radiation left over from the very birth of everything. This is called the intergalactic medium, and though it is far thinner than anything we could recreate in a laboratory on Earth, it is there, drifting, connecting one galaxy to another in a way that is subtle but real. Nothing in the universe, it turns out, is truly perfectly alone. But there are limits even to what we can see. The observable universe has a horizon, an edge beyond which light simply has not had time to reach us since the universe began. Because the universe is roughly 13.8 billion years old, and because light travels at a fixed and finite speed, there is a boundary to how far our vision can reach. Beyond that horizon, there may be more galaxies, more clusters, more voids, stretching on perhaps forever, but we will never see them, not because they aren't there, but because their light has not yet had the time to complete the journey to us. It is a gentle reminder that even the vastness we can imagine is only a fraction of what may truly exist. A single page in a book whose full length we cannot know. And this observable universe is not static. It is growing. The expansion of the universe is accelerating, meaning that space itself is stretching, carrying galaxies away from one another at a rate that increases with time. This isn't galaxies moving through space the way a ship moves through water. It is space itself expanding, like a slowly inflating balloon with dots painted on its surface, each dot representing a galaxy, moving apart from every other dot not because any of them are swimming away, but because the very fabric between them is stretching thinner. And this stretching is speeding up, driven by a mysterious force we call dark energy, a force we can measure but do not yet fully understand. Because of this accelerating expansion, the universe is becoming more isolated over time. Distant galaxies are slowly slipping beyond our horizon, their light one day destined to become too stretched, too faint, too delayed to ever reach us. Billions of years from now, an observer in our galaxy looking out into the night sky may see only the stars of their own galactic neighborhood, with nothing beyond, the rest of the universe having drifted silently out of view. It is a strange and quiet kind of forgetting, written not into memory, but into the geometry of space itself. And so, against this backdrop of expanding, isolating vastness, we find a curious thread of connection running through nearly every galaxy we have studied. Every large galaxy has a giant black hole, not a small one, not an ordinary stellar remnant. A supermassive black hole, sitting quietly at the very center, sometimes millions of times the mass of our sun, sometimes billions. Our own Milky Way has one, a black hole we call Sagittarius A star, resting silently at the galactic core, invisible, patient, and ancient. Nearly every large galaxy we have ever observed carries one of these giants within it, hidden in the heart of its spiral arms or its great elliptical glow, like a seed at the center of vast blooming flower. And this is where our question begins to take shape. If nearly every galaxy holds one of these enormous black holes at its heart, and if galaxies themselves are connected into vast structures, clusters, filaments, and webs that span the observable universe, then perhaps the black holes are not simply isolated points of gravity, sitting alone in their galactic homes. Perhaps they are part of something larger. Perhaps, across unimaginable distances, they are connected. Let that thought settle over you now, gently, the way a soft blanket settles over shoulders on a cold night. Somewhere out there, in the dark spaces between galaxies, a question is waiting. Are these giants truly alone? Or are they, in some way we are only beginning to understand, whispering to one another across the void? Rest here for a moment. Let your breathing slow further. There is no need to hold on to every fact, no need to remember every number or name. Let them drift past you like distant lights seen from a train window at night, beautiful, brief, and gone. In the next part of our journey, we will follow these black holes deeper, into the very heart of galaxies, and begin to understand what it might mean for them to reach across the emptiness and touch one another. For now, simply rest and let the universe, in all its vastness, hold you gently within it. Not every galaxy has the same kind of black hole. When we imagine a black hole, we often picture a single, uniform kind of monster, dark and simple, always identical to the last. But the truth is far more varied, far more textured, like snowflakes that all seem the same from a distance yet differ completely up close. Some galaxies host black holes so enormous they defy easy comprehension, while others hold black holes so modest they barely seem to belong to the same family of objects. The universe, it seems, does not believe in uniformity, prefers variety, even among its darkest creations. Even the smallest galaxies are not excluded from this pattern. Tiny dwarf galaxies can also host black holes. You might imagine that only the great sprawling spirals and giant ellipticals, the grand cathedrals of the galactic world, would have enough mass, enough gravity, enough sheer presence to cradle a black hole at their center. But dwarf galaxies, small collections of stars that might contain only a few 100 million suns compared to the hundreds of billions in larger galaxies, have been found to harbor black holes of their own. It is a little like discovering that even the smallest village, tucked away in a quiet valley, has its own ancient well, deep and dark, reaching down into the earth just as the wells of great cities do. Scale, it turns out, is not a requirement for mystery. And within this variety, some black holes are surprisingly small. When astronomers speak of stellar black holes, the kind formed from the collapse of a single massive star, they are often speaking of objects only a few times the mass of our sun. Compressed into a space smaller than a city, these black holes are almost delicate in comparison to their supermassive cousins, and yet they are no less real, no less strange, no less capable of bending space and time around themselves. It is strange to think that something so small, in cosmic terms, could still hold such absolute power over anything that ventures too close. Between these small stellar black holes and the supermassive giants at galactic centers lies a gap, a strange and quiet gap that scientists have long wondered about. And this leads us to another gentle mystery. There may be intermediate-sized black holes, objects that bridge the space between the small and the immense. For years, evidence for these in-between giants was frustratingly elusive, glimpsed only faintly, hinted at through subtle gravitational clues, like footprints in sand that the tide keeps almost erasing. Slowly, over recent years, more solid evidence has emerged, suggesting that these intermediate black holes truly do exist, scattered quietly throughout the universe, waiting in the spaces between categories, comfortable in their own quiet ambiguity. And then there are the giants, the true giants, that make even supermassive black holes at the centers of ordinary galaxies seem small by comparison. The largest known black holes contain tens of billions of solar masses, meaning tens of billions of times the mass of our own sun, compressed into a single point of unimaginable density. If you tried to picture the scale of such an object, you might imagine standing before something so vast that light itself seems to hesitate at its edges, bending, slowing, struggling against a gravity so overwhelming it reshapes the geometry of space around it. These ultramassive black holes tend to sit at the hearts of the largest galaxies in the universe, ancient and enormous, silent monuments of gravity that have grown for billions upon billions of years. Speaking of time, it is worth pausing here to consider just how old some of these objects truly are. The first black holes formed billions of years ago, not long, in cosmic terms, after the universe itself began. When the first massive stars ignited and burned through their fuel in a matter of millions of years, rather than billions, some of them collapsed under their own gravity, forming the very first black holes the universe had ever known. These early black holes were born into a much younger, much hotter, much stranger universe than the one we see today, a universe still cooling from its explosive beginning, its first structures only beginning to take shape. But here is where the story becomes even stranger, even more delicate. Some black holes may have been born before the first stars. This is one of the more curious and quietly debated ideas in modern astronomy, the possibility that in the earliest fractions of a second after the universe began, tiny fluctuations in the density of the newborn cosmos could have collapsed directly into black holes, without ever needing a star to form and die first. These hypothetical objects, sometimes called primordial black holes, may have emerged from the raw fabric of the early universe itself, long before the first points of starlight ever began to shine. If they exist, they would be among the oldest objects in all of creation, silent witnesses to a universe that had not yet learned how to make light. And yet, despite their age, despite their power, despite their immense gravitational influence, we must remember one of the strangest truths about black holes themselves. Black holes are invisible by nature. Their gravity is so intense that not even light, the fastest thing in the universe, can escape their pull once it crosses a certain boundary. This means that a black hole, by definition, cannot be seen directly. There is no surface to reflect light, no glow to catch in a telescope, only an absence, a place where light disappears and never returns. It is one of the great paradoxes of astronomy that some of the most powerful and influential objects in the universe are also, in a very literal sense, the most invisible. So how, then, do we know they are there at all? Black holes can be detected by their shadows. Around many black holes, matter gathers into a swirling disk before it falls inward, glowing brightly as it heats up under the intense pressure and friction of its final descent. Astronomers can observe this glowing material, and within it, they can see a dark, perfectly circular silhouette, the shadow cast by the black hole's gravity bending light around it. It is a bit like standing in a well-lit room and noticing a strange, perfectly dark circle hovering in the air, knowing that whatever casts a shadow that clean and that complete must be something extraordinary indeed. Through this shadow, astronomers can measure a black hole's size, its mass, and even confirm its very existence, without ever seeing the black hole itself, only the shape it leaves behind in the light around it. And remarkably, this is no longer only theory. We have actually taken a picture of a black hole. In 2019, an international collaboration of astronomers combined the power of telescopes spread across the entire planet to create something called the Event Horizon Telescope, effectively turning the whole Earth into a single enormous instrument. Pointed at the supermassive black hole at the center of a distant galaxy called M87, This network of telescopes captured a now famous image, a soft, glowing ring of orange light surrounding a dark, silent center. It was the first time in human history that our species had ever truly seen, with our own instruments, the shadow of a black hole. Years later, astronomers achieved the same feat again, this time capturing an image of Sagittarius A star, the black hole resting quietly at the heart of our very own Milky Way. Think about that for a moment, softly, without straining. Somewhere at the very center of our galaxy, invisible and silent, there is a black hole whose shadow we have now seen with our own eyes, translated through light and mathematics and the patient work of scientists across the globe, into a picture we can hold in our minds. It is strange to think that something so dark, so hidden, so fundamentally invisible could ever be captured in an image at all. And yet it was. Out of pure darkness, we found a way to see. As you rest here now, let yourself imagine that image, softly glowing. A ring of light wrapped gently around an endless dark center. There is no need to hold on to every detail. Simply let this thought settle over you like the horizon of the black hole itself, a boundary between what we can know and what remains hidden, comforting in its mystery rather than frightening. In the next part of our journey, we will begin asking what happens at the very edge of that darkness, and what it might mean for these silent giants to reach beyond their own galaxies, into the space between. For now, let your breathing slow. Let your thoughts drift like light bending gently around some distant, unseen center, and rest. We have looked at black holes from a distance now, seen their variety, their strange history, even glimpsed a photograph of one taken from the shadow they leave in light. But to understand whether these giants might reach across the universe and touch one another, we need to step closer, gently, and understand what a black hole actually does to the space and time around it. So let your mind drift inward now, past the safety of distance, toward the strange and quiet physics at the very edge of one of these giants. The first thing we should release softly is a common misunderstanding. Black holes don't actually suck everything in. It is easy to imagine them as cosmic vacuum cleaners, restlessly pulling in anything that drifts too close. But this isn't quite true. A black hole's gravity works the same way any other object's gravity works, following the same gentle rules that keep your feet on the ground or the moon in orbit around the Earth. If our sun were somehow replaced with a black hole of the exact same mass, the Earth would continue orbiting exactly as it does now, undisturbed, unthreatened, simply circling a different kind of darkness. It is only very close to a black hole within a certain boundary that its gravity becomes so extreme that nothing can escape. Beyond that boundary, a black hole behaves like any other massive object, patient and predictable, not some hungry force reaching out to devour everything nearby. To understand why black holes behave this way, we have to go back to an idea first proposed over a century ago. Einstein predicted space-time could bend. Before Einstein, gravity was often imagined as an invisible force reaching out between objects, pulling them toward one another across empty space. But Einstein offered something stranger and something far more beautiful. He proposed that space and time are not simply a stage on which objects move, but a fabric, flexible and responsive, that can bend and curve in the presence of mass. Imagine a stretched sheet, smooth and flat, and then imagine placing a heavy stone at its center. The sheet dips and curves around the stone, and anything rolling nearby will naturally curve along with it, not because the stone is reaching out and pulling, but because the very shape of the space around it has changed. This is gravity in Einstein's vision, not a pull but a curve, an elegant bending of the universe itself around anything with mass. And a black hole, with all of its immense concentrated mass, warps this fabric of space-time more dramatically than almost anything else we know. But here is something quieter, something that stretches our understanding even further. Black holes may warp more than just space. Some theoretical work suggests that the intense gravity near a black hole may influence quantum fields, may ripple outward in gravitational waves that carry information about entire cosmic events, may even, in extreme and still poorly understood ways, touch the very fabric of physical law itself at its boundary. We do not yet fully understand where the ordinary rules of physics end and the truly unknown begins when we approach these silent giants closely enough. It is a reminder that at the edge of a black hole, we are standing at the edge of our own knowledge as well. That edge has a name, and a very precise one. The event horizon is the point of no return. This is the invisible boundary surrounding a black hole, the line beyond which gravity becomes so overwhelming that nothing, not light, not matter, not even information itself, can ever escape once it crosses through. It is not a physical surface, not something you could touch or bump against. It is simply a mathematical boundary, a threshold in the geometry of space-time itself, beyond which the universe as we understand it effectively ends. Crossing the event horizon is not a violent event, not an instant of destruction. From the perspective of whatever crosses it, nothing dramatic would necessarily seem to happen at all in that very moment. And yet, from that point onward, there would be no path back, no direction that leads outward again, only inward, deeper into the darkness, forever. As you approach this boundary, something else begins to happen, something that touches not just space but time itself. Time behaves strangely near black holes. According to Einstein's equations, gravity does not only bend space, it also bends time, slowing it down in regions where gravity is strong. Near a black hole, this effect becomes extreme. An observer watching from a safe distance would see time for anything approaching the event horizon slow down more and more, appearing almost to freeze at the boundary itself, its motion stretching out infinitely, its light growing dimmer and dimmer, redder and redder, fading toward invisibility without ever quite seeming to fully arrive. Meanwhile, for whatever is actually falling inward, time would feel completely normal, flowing at its usual gentle pace, even as the outside universe, watched from within that fall, would appear to race forward, faster and faster, centuries passing in moments. Two perspectives, two experiences of time, both true, both real, simply seen from different positions within the curved fabric of space-time. And near this boundary, light itself begins to behave in ways that feel almost impossible. Light can orbit a black hole. At a very specific distance from the event horizon, called the photon sphere, gravity becomes strong enough that light can actually travel in a circular path, endlessly orbiting the black hole without ever falling in or escaping outward, caught in a perfect, precarious balance. Imagine light, the fastest and most fundamental thing in the universe, quietly circling forever, trapped not by walls or barriers, but simply by the shape of space itself. It is a strange, beautiful stillness at the heart of so much extremity. And even beyond this photon sphere, gravity continues to shape the path of light in gentler ways. Gravity can bend light around a black hole. Light passing near, but not too near, a black hole will curve slightly along its journey, following the gentle warp of space-time the same way a marble might curve slightly if rolled near the edge of a shallow depression. This bending allows black holes to act almost like enormous cosmic lenses, distorting and magnifying the light of stars and galaxies that happen to lie behind them, sometimes creating strange, warped, multiple images of the very same distant object, smeared and curved around the darkness at the center like light bending gently around the edge of a raindrop. Black holes are not simply still points of gravity either. Many of them are spinning, and spinning with astonishing speed. Black holes can spin at incredible speeds, some rotating so quickly that their outer boundary moves at a significant fraction of the speed of light itself. This spin is often inherited from the star or the material that originally collapsed to form the black hole, conserved and concentrated as everything compresses down into an impossibly small space. A spinning black hole doesn't just sit in space-time, it drags space-time along with it, twisting the fabric of the universe in its immediate surroundings the way a spoon might drag and swirl the surface of a cup of tea. Because of this, the shape of a black hole depends on its spin. A black hole that isn't spinning at all takes on a perfectly simple, perfectly spherical event horizon. But a rapidly spinning black hole becomes flattened, its event horizon bulging outward at its equator, the way the Earth itself bulges very slightly at its own equator due to its rotation, though on a scale and to a degree far more extreme. The faster the spin, the more dramatic this flattening becomes, until the black hole's very geometry is shaped as much by its rotation as by its mass. And this spin does not stay contained within the black hole itself. It reaches outward, influencing everything nearby. A black hole's gravity can twist the orbits of nearby objects, dragging the surrounding space-time along with its rotation in an effect known as frame dragging. Stars, gas, and matter orbiting near a spinning black hole don't simply circle it in a clean, stable path. Their orbits are gently twisted, pulled along in the direction of the black hole's spin, swept up in a slow, silent choreography dictated not by any force reaching out to grab them, but by the very shape of the space they are moving through, a shape the black hole itself has quietly, patiently woven around it. Let this thought settle over you now, slowly. A black hole is not a hungry mouth reaching outward to consume. It is something closer to a sculptor, patiently shaping the space-time around it, warping distances, slowing time, bending light, twisting the paths of everything nearby, not through force, but through the sheer, quiet weight of its own existence. It reshapes its surroundings simply by being there. In the same gentle way a heavy stone reshapes the sheet it rests upon, without ever reaching out, without ever needing to. Rest now in this image. Space curving, time slowing, light bending softly around an endless dark center. There is nothing here to fear, only to wonder at, the same wonder you might feel standing at the edge of a vast, still lake at night, aware of depths you cannot see, yet calm in their presence. In the next part of our journey, we will begin to ask how these individual, spinning, light-bending giants might reach beyond their own galaxies entirely, and what threads might connect one to another across the emptiness between them. For now, let your thoughts settle, let your breathing slow further still, and rest here, quietly, at the edge of the dark. We spoke of black holes shaping space and time simply by existing, sculptors rather than devourers. But sculptors, it turns out, are not always silent. Some of these giants reach outward in ways far more dramatic than a gentle curve in space-time, and to understand how they might connect to the wider universe, we need to see what happens at their most active, most energetic edges. Around many black holes, especially those actively pulling in matter, there exist magnetic fields around black holes that are incredibly powerful, some of the strongest magnetic fields found anywhere in the universe. As gas and dust spiral inward toward the event horizon, the charged particles within that swirling material generate immense magnetic forces, twisting and coiling around the black hole like invisible ribbons wound tightly around a spinning top. These fields can grow so intense that they begin to shape the behavior of everything nearby, channeling matter, focusing energy, and setting the stage for some of the most spectacular displays in the cosmos. Because of these powerful magnetic fields, some black holes launch enormous jets, Streams of superheated particles blasted outward from their poles at speeds approaching the speed of light itself. These jets can stretch for thousands, even millions of light years, far beyond the edges of the galaxies that contain them, glowing brightly enough to be detected across the vast emptiness of intergalactic space. Picture a lighthouse beam, narrow and brilliant, except instead of sweeping gently across dark water, it pierces straight through the void between galaxies, a thin, glowing thread connecting the heart of one galaxy to the emptiness far beyond its edges. It is a strange thought to hold quietly in the mind, that something born from pure darkness could produce light bright enough to outshine an entire galaxy, and reach so very, very far. And these jets are not always fixed in place. Black holes can change direction, their spin axis gradually shifting over time as they merge with other black holes, or as the swirling disk of material around them tilts and reorients itself. When this happens, the jets shift along with it, sweeping slowly across the sky over thousands or millions of years, like the beam of a lighthouse turning ever so slowly to face a new direction. Astronomers have found evidence of this in some galaxies, faint ghostly remnants of old jets pointing one way, with brighter, newer jets emerging at a different angle entirely, silent records of a black hole quietly changing its orientation over unimaginable stretches of time. Within this swirling, twisting, magnetically charged environment, something else remarkable occurs. Black holes can act like natural particle accelerators, flinging charged particles to extraordinarily high energies, far beyond anything we can achieve even with our most powerful instruments here on Earth. The combination of intense gravity, powerful magnetic fields, and rapidly spinning space-time creates conditions capable of hurling protons and electrons outward at speeds and energies that stagger the imagination. Some of these particles eventually reaching us, here on our quiet planet, as faint traces of cosmic rays, tiny messages carried across unimaginable distances from the edge of some distant black hole's chaotic embrace. But not everything that approaches a black hole is flung outward. Some things wander too close, and their stories unfold very differently. Stars can wander close to a black hole, drawn inward by the same gentle curve of gravity that shapes the orbits of everything nearby. In crowded regions of a galaxy, particularly near the busy, densely packed center where a supermassive black hole resides, stars occasionally drift onto orbits that bring them dangerously near this invisible giant, caught in a slow, patient dance that may end quietly, or may end in something far more dramatic. Remarkably, some stars survive encounters with black holes, passing close enough to feel the immense pull of gravity, perhaps having their outer layers gently stripped away, perhaps having their shapes stretched and distorted by tidal forces, and yet emerging still intact, continuing onward into the darkness, forever changed but not destroyed. It is a little like a ship passing through a violent storm, battered and reshaped by the encounter, sails torn, hull scarred, yet still afloat, still sailing onward into calmer waters beyond. Other stars are not so fortunate. A black hole can tear apart an entire star, an event astronomers call a tidal disruption, when a star wanders so close that the black hole's gravity pulls far more strongly on the near side of the star than the far side, stretching it thinner and thinner until it is torn completely apart, its material spiraling into a bright, glowing stream around the black hole before slowly being consumed. These events release enormous bursts of light, sometimes outshining the rest of the entire galaxy for a brief time, a final, brilliant farewell from a star whose long life ends not in a quiet fade, nor in an explosive supernova, but pulled apart thread by thread, gently and completely, by the patient gravity of something it could not resist. And it is not only stars that fall within reach of this pull. Black holes can capture wandering planets, rogue worlds that have drifted free from their original stars, wandering silently through interstellar space, occasionally passing close enough to a black hole to be captured into a slow, cold orbit. Unlike a star, A planet swept into such an orbit would not be torn apart, not immediately, but would instead become a strange, silent companion, circling a source of gravity that gives off no light, no warmth, nothing but its own quiet, invisible presence. A planet, once perhaps warmed by a distant sun, now drifting forever through darkness, orbiting a giant it can never see. Given how invisible black holes are, how do we know so much about them at all? About their spins, their jets, their magnetic fields, their captured stars and shredded worlds. Astronomers measure black holes without visiting them, relying instead on the careful, patient observation of everything around them. The glowing disks of infalling matter, the bending of background starlight, the motion of stars and gas caught in their gravitational embrace, the faint gravitational waves rippling outward when two black holes finally merge. It is a bit like understanding the shape and size of a whirlpool not by diving into its center, but by watching carefully how leaves and twigs circle and are pulled inward at its edges, learning its nature entirely through its effect on everything nearby. And in learning about black holes this way, astronomers have found something remarkable. Black holes help astronomers test Einstein's theory, offering some of the most extreme laboratories in the entire universe for examining whether Einstein's ideas about gravity, about the bending of space and time, truly hold up under the most intense conditions imaginable. Every observation of a black hole, every bent beam of light, every gravitational wave detected from a distant merger, every star caught twisting in complex, warped orbits near a galactic center, offers another chance to test these century-old equations against reality itself. And so far, remarkably, patiently, again and again, the universe continues to agree with what Einstein once wrote down using nothing more than mathematics, imagination, and a quiet, careful mind. Let this settle over you now. Black holes are not simply dark, silent points sitting alone in the void. They are dynamic, active, capable of launching light-years-long jets, capable of tearing apart entire stars, capable of capturing wandering worlds, capable of accelerating matter to speeds that stagger the imagination. And yet, for all of this fierce activity, they remain patient teachers as well, quietly allowing us, from a great and careful distance, to test the very laws that shape our universe. Rest now in the stillness between these two truths, the fierce and the patient, existing together at the heart of every one of these giants. There is nothing here to fear, only to observe softly, from a great and comfortable distance, the way you might watch a distant storm over the ocean, powerful and vast, yet entirely unable to reach the quiet safety of the shore where you rest. Let your body settle once more into stillness, and let your breathing find that same slow, familiar rhythm. We left our giants resting quietly, fierce and patient at once, tested again and again by the light and gravity of everything around them. Now let us step back gently from any single black hole, and look instead at the environment they live within, the crowded, restless heart of a galaxy, where feeding, resting, and growth unfold across timescales far beyond a single human life. The centers of galaxies are extremely crowded, far more so than the quiet outer regions where stars like our sun drift in wide, gentle orbits. Near the very heart of a large galaxy, stars can be packed together far more densely, sometimes millions of times closer than in our own solar neighborhood, along with vast reservoirs of gas, dust, and drifting stellar remnants, all swirling slowly around the supermassive black hole that anchors the center. If the outer galaxy is like a quiet countryside, spacious and calm, the galactic center is like the dense heart of an ancient city, streets narrow, buildings pressed close together, life and motion woven tightly into every corner. Within this crowded environment drifts a fine, quiet material that plays a surprisingly important role. Cosmic dust helps feed black holes, spiraling slowly inward from the surrounding galaxy, drawn by gravity into thinner and thinner streams as it approaches the black hole's domain. This dust, made of tiny grains formed in the winds of dying stars and the debris of ancient supernovae, drifts gently through the crowded galactic center like fine mist settling slowly toward a drain, patient and unhurried, taking sometimes millions of years to complete its long, slow fall inward. And it is not only dust that feeds these giants. Some black holes grow by swallowing gas clouds, vast drifting clouds of hydrogen and helium that occasionally wander too close to the galactic center, torn apart by gravity and stretched into long, glowing streamers before spiraling down toward the event horizon. Astronomers have watched this happen in real time in a few remarkable cases, observing a gas cloud slowly being pulled apart, its material stretching thinner and thinner across the sky, a quiet, glowing thread being drawn steadily into darkness over the course of just a few careful years of observation. Because feeding depends on there being enough material nearby, black holes can have feeding seasons, periods when gas and dust are especially abundant near the galactic center, followed by longer stretches when very little material drifts close enough to fall inward. During an active feeding season, a black hole may brighten considerably, its surrounding disk glowing fiercely as matter spirals inward and heats to enormous temperatures. But such seasons do not last forever, and eventually, the nearby material becomes depleted, sparse, and scattered, leaving the black hole with less and less to consume. When this happens, black holes can remain quiet for millions of years, sitting largely dormant at the center of their galaxy, their presence betrayed only by the gentle gravitational influence they hold over the stars orbiting nearby, rather than by any bright glow of infalling matter. A quiet black hole is, in many ways, indistinguishable from the empty darkness around it, patient and undetected, waiting through long stretches of cosmic time for the slow drift of gas and dust to once again bring it something to feed upon. Even our own galaxy's great giant follows this same quiet pattern. The Milky Way's black hole occasionally wakes up, flaring briefly brighter as small clumps of gas or dust drift close enough to be pulled inward, producing faint bursts of light and X-ray radiation that astronomers have observed drifting outward from the very center of our galaxy. For the vast majority of the time, Sagittarius A star rests in near silence, dim and undisturbed, but every so often, quietly, without warning, it seems to stir, consuming some small wandering morsel of gas before settling back once more into its long and patient rest. In more dramatic cases, especially in the distant, early universe, this feeding becomes so intense and sustained that some galaxies shine because of feeding black holes, their entire centers blazing with light far brighter than all of the galaxy stars combined. These extraordinarily bright galactic centers are called quasars, and they represent some of the most luminous single objects in the entire universe, powered not by starlight, but by the immense energy released as matter spirals down into a supermassive black hole at tremendous speed, heating to unimaginable temperatures in the final moments before crossing the event horizon. A single quasar, born from a hungry black hole feeding voraciously in the crowded heart of a young galaxy, can outshine every one of the billions of stars surrounding it combined. This feeding, this fierce and occasional brilliance, does not remain contained to the galactic center alone. Black holes can influence star birth, their jets and radiation reaching outward through the surrounding galaxy, sometimes compressing nearby clouds of gas and triggering the collapse that gives birth to new stars, and other times heating and scattering that same gas so thoroughly that star formation is suppressed entirely across wide regions of the galaxy. It is a strange and delicate balance, the same giant capable of nurturing new stars in one era, and quietly starving entire regions of a galaxy of the material needed for star birth in another, its influence stretching far beyond the reach of its own gravity alone. Because of this far-reaching influence, black holes may influence the growth of galaxies themselves, shaping how large a galaxy ultimately becomes, how quickly it forms new stars, and even how its overall structure evolves across billions of years. Astronomers have noticed a curious pattern, that the mass of a galaxy's central black hole often correlates closely with the mass of the entire galaxy surrounding it, as though the growth of the giant at the center and the growth of the galaxy as a whole are quietly, patiently linked, each shaping the other across the long unfolding of cosmic time, in a relationship we are still working to fully understand. But black holes and the crowded, glowing hearts of galaxies are not the only unseen force shaping this vast structure. There is something else, something even less visible than the black holes themselves. Dark matter holds galaxies together, an invisible form of matter that neither emits nor absorbs light, detectable only through its gravitational influence on the stars, gas, and galaxies around it. Without dark matter's quiet, unseen gravitational pull, galaxies would not have enough mass to hold their stars in stable orbits at all, and would likely have drifted apart entirely, long before life or light or any of these questions we ask tonight ever had the chance to exist. Dark matter forms vast, invisible halos around galaxies, unseen scaffolding within which the visible stars, dust, gas, and even the giant black holes at galactic centers all quietly reside. Let this settle over you gently now. Beneath every glowing quasar, every crowded galactic center, every feeding season and quiet dormant stretch of millions of years, there lies an entire invisible framework of dark matter, holding everything together in ways we still do not fully understand, patient and silent, felt only through its gravity, never through its light. And within this framework, black holes rise and rest, feed and starve, brighten and dim, in long, slow cycles that stretch across cosmic time, shaping not only their own galaxies, but perhaps, as we will soon explore, reaching even further into the space between one galaxy and the next. Rest here for a while. There is nothing to hold onto tightly, only images to let drift softly through your mind. A crowded galactic center, dust falling slowly inward like fine mist. A black hole waking briefly, then resting again for millions of years. An invisible framework of dark matter, cradling galaxies gently across unimaginable distances. Let your breathing slow further, let your thoughts loosen their grip on wakefulness, and rest within this quiet, patient darkness. As the universe continues its long, slow work, entirely without needing you to stay awake to witness it. Let your body soften once more, sinking deeper into whatever surface holds you now. We have watched a black hole feed and rest, brighten and dim, shaping and being shaped by the galaxy around it. Now let us widen our view once more, out past the edges of a single galaxy entirely, and watch what happens when galaxies themselves begin to move, to reach and eventually to meet. Galaxies grow by eating smaller galaxies, a slow and quiet process that unfolds over hundreds of millions of years. When a smaller galaxy drifts too close to a larger one, gravity begins to pull at its edges, stretching its stars and gas into long, faint streams that wrap gently around the larger galaxy before gradually being absorbed entirely. It is not a violent collision in the way we might picture a crash, but something closer to a slow embrace, one galaxy gently unraveling into another across a span of time so vast that entire civilizations could rise and fall before the process ever completed. Our own Milky Way carries the faint traces of many such ancient meals, ghostly streams of stars still visible in its outer reaches, remnants of smaller galaxies absorbed long before our sun ever began to shine. Even when two galaxies do not merge completely, they can still shape one another. Galaxies can steal material from one another, gravity reaching across the space between them and slowly drawing gas, dust, and even stars away from a smaller or looser companion. This stolen material often forms long, delicate bridges and tails, faint filaments of stars and gas stretched between two galaxies like threads pulled loose from fabric, glowing softly in the dark, silent evidence of an encounter that reshaped both galaxies involved, even if neither one fully consumed the other. This is not simply an ancient story either. It is happening still, quietly, even now, close to home. The Milky Way is slowly heading toward Andromeda, our nearest large galactic neighbor, the two of us drawn together by gravity across a gulf of over 2 million light-years. In a few billion years, our galaxy and Andromeda will begin to merge, their stars and gas slowly intermingling, their spiral shapes gradually dissolving into something new, a single larger galaxy, sometimes imagined and nicknamed Milkomeda. And at the heart of each galaxy, patiently waiting through this vast, slow dance, rests a supermassive black hole, carried along with its galactic home, toward an eventual meeting with its counterpart. Because when two galaxies merge, their central black holes eventually find each other as well. Black holes can merge together, drawn by gravity into a slow spiral around one another, orbiting closer and closer over millions of years until, in a final dramatic instant, they collide and combine into a single larger black hole. This is one of the most violent and energetic events the universe is capable of producing, more powerful in that brief final moment than the combined light of every star in every galaxy in the observable universe, and yet it releases almost no visible light at all. Instead, it releases something else entirely, a form of energy that does not travel as light, but as motion itself, rippling outward through the very fabric of space and time. Gravitational waves ripple across the universe, tiny distortions in space itself, stretching and compressing everything they pass through by an almost immeasurably small amount, yet carrying within them the story of the violent event that created them. When two black holes finally merge, they send these ripples outward in every direction, spreading across the universe like circles expanding outward from a stone dropped into still water, except the water here is space-time itself, and the ripples, though impossibly faint by the time they reach us, can still be measured by sufficiently sensitive instruments here on Earth. In the final moments before two black holes merge completely, something remarkable happens to the newly formed giant they create. Black holes can ring like a bell, the newly merged black hole briefly vibrating, its event horizon oscillating and settling into its final, stable shape, releasing one last distinct pattern of gravitational waves as it does, a sort of cosmic chime marking the final settling of two giants becoming one. Scientists can study this ringing to learn about the size, the spin, and the nature of the newly formed black hole, listening, in a sense, to the sound of space-time itself finding its balance again after such an immense disturbance. These ripples, once created, do not arrive instantly. Gravity travels at the speed of light, meaning that just as light from a distant merger takes time to reach us, so too does the gravitational disturbance itself, spreading outward no faster than light can travel. A merger that occurred 1 billion light-years away sends its gravitational ripple outward for 1 billion years before it ever reaches our small, quiet planet, arriving finally as the faintest of trembles, so subtle that detecting it required building some of the most sensitive instruments human beings have ever created. And not every black hole remains anchored quietly at the center of its galaxy either. Black holes can wander through space, sometimes flung outward from their original galactic home by the very force of a merger itself. The newly combined black hole given a gentle gravitational kick that sends it drifting away from the galactic center, sometimes even ejected from the galaxy entirely, doomed to wander alone through the vast emptiness between galaxies for the rest of time, carrying no light, no stars, no galaxy along with it, simply drifting, invisible and silent, through the dark. This wandering fits within a much larger pattern as well. Galaxies are constantly moving, drifting, orbiting, merging, and separating across the universe, none of them truly fixed in place, all of them caught in the same slow, patient dance shaped by gravity across unimaginable stretches of time. Even galaxies that appear motionless to us, fixed points of light in our night sky, are in truth moving at tremendous speeds, simply so distant that their motion becomes imperceptible across the short span of a human lifetime, the way a distant ship on the horizon might seem still, even as it steadily makes its way across the sea. And within all of this motion, all of this merging and drifting and wandering, there exists a strange and delicate balance. There is a boundary where gravity balances, a point between two massive objects, whether two galaxies, two black holes, or even two stars, where their combined gravitational pulls momentarily equal one another, creating a stable, quiet point of equilibrium. Objects can sometimes settle into orbits around these balance points, caught gently between two competing pulls, neither one fully winning, resting instead in a delicate, quiet harmony, held in place not by the strength of either force alone, but by the careful, patient balance between them. Let this image settle over you now, softly. Two galaxies, drifting slowly closer across billions of years. Two black holes at their hearts, spiraling nearer, patient and unhurried, until finally, they meet, merge, and ring quietly outward across the universe in ripples of pure gravity, felt lightly, gently, a billion years later, on a small and quiet world. Nothing in this universe is ever truly still. Everything drifts, merges, and settles, again and again, into new and quiet forms of balance. Rest here now in that same slow drifting motion. There is no need to hold onto anything tightly, no need to chase after every merging galaxy or every rippling wave. Simply let your thoughts move the way the universe moves, slowly, patiently, without any hurry to arrive anywhere at all. In the next part of our journey, we will begin asking what all of this drifting, merging, and connecting might mean, and whether these countless quiet unions could somehow link even the most distant black holes together, across the vast, dark space between every galaxy. For now, let your breathing slow, let your body rest, and drift gently into the dark. Let your body settle deeper now, into whatever soft surface is holding you. We have watched galaxies merge, black holes collide, ripples of gravity spreading outward across the universe like sound settling after a distant chime. Now let us drift even further outward, past galaxies entirely, into the quiet fabric of the universe itself, and ask what fills the space between everything and what lies hidden beneath even that. The universe is filled with background radiation, a faint, ancient glow left over from the very earliest moments after the universe began. This radiation, sometimes called the cosmic microwave background, is the oldest light we can observe, released when the universe was only a few 100,000 years old, finally cool enough for light to travel freely for the very first time. It surrounds us in every direction, a soft, faint whisper of heat left over from creation itself, filling every corner of space, even the vast emptiness between galaxies, with a gentle warmth so faint it sits only a few degrees above absolute zero. Imagine the last embers of a great fire, long since burned down, still faintly warm to the touch even after the flames themselves are gone. That is this radiation, the quiet afterglow of the universe's own beginning, still gently present, everywhere, all at once. And yet, for all that we can observe, so much of what fills the universe remains hidden from us entirely. The universe is mostly invisible, made up overwhelmingly of dark matter and dark energy, two mysterious components that together account for the vast majority of everything that exists, while ordinary matter, the stars, the planets, the galaxies, the very atoms that form our bodies, makes up only a small fraction of the total. We are, in a very real sense, surrounded by a universe we can barely see, drifting through vast reservoirs of matter and energy that shape everything around us, and yet remain almost entirely undetectable, except through their subtle gravitational influence. Even the seemingly empty space between galaxies carries more than we might expect. Even empty intergalactic space contains magnetic fields, faint and diffuse, stretching across unimaginable distances, remnants perhaps of ancient processes from the universe's early history, or generated slowly over time by the movement of charged particles drifting through the vast, thin gas that fills the space between galaxies. These fields are almost unimaginably weak compared to anything we experience here on Earth, and yet they exist, quiet and pervasive, another subtle thread woven through the seemingly empty dark. Within this vast structure, there exists a fundamental limit that shapes everything. The universe has a speed limit, the speed of light, a boundary that nothing with mass can ever reach or exceed. This isn't simply a matter of needing a more powerful engine or a cleverer design. It is a fundamental property of the universe itself, woven into the very geometry of space and time, the same geometry that black holes bend and curve so dramatically at their edges. Light moves at this limit because it has no mass at all, while everything else, every star, every planet, every particle of dust, remains forever bound beneath it, no matter how much energy might be applied. And yet, even at this fundamental level, where light itself becomes the measure of what is possible, we find another quiet strangeness. Empty space isn't truly empty. Even in a region utterly devoid of matter, of light, of any particle at all, tiny quantum fluctuations continue to occur, fleeting pairs of particles winking briefly into existence before vanishing again almost instantly, a soft, constant simmer at the very base of reality itself. This is not something we can observe directly with our eyes, but its effects have been measured carefully in laboratories here on Earth. A quiet confirmation that even the emptiest space is never entirely perfectly still. Returning our thoughts to the black holes at the center of so much of tonight's journey, we find that they may hold a secret stranger than anything we have discussed so far. Black holes store an enormous amount of information, far more, in fact, than seems possible given their size. Every particle, every star, every fragment of matter that has ever fallen into a black hole carries with it a vast amount of information, and rather than simply vanishing, physicists believe this information must somehow be preserved, tucked away within the black hole itself, even though nothing can ever emerge from within it again. But if nothing can escape a black hole, where could this information possibly be kept? Information may be stored on a black hole's surface, not within its depths, but somehow encoded across the two-dimensional surface of its event horizon, like a shadow holding the full shape of everything it represents. This strange idea that a black hole's boundary might act almost like a hologram, storing the complete information of everything that has ever fallen within it, has quietly reshaped how physicists think about the deepest nature of space, time, and information itself, suggesting perhaps that the universe we experience as three-dimensional might, at its most fundamental level, be encoded upon a much simpler, flatter foundation. This leads to even stranger territory still. Some theories suggest space-time has a microscopic structure, that if we could examine the fabric of the universe at an unimaginably small scale, far smaller than any atom, we might find that it is not smooth and continuous at all, but instead grainy, textured, built from tiny discrete units. The way a photograph that appears smooth from a distance reveals itself to be made of countless individual pixels upon close inspection. At this scale, space and time themselves might not be a seamless backdrop, but something closer to a fine, quiet weave, its individual threads far too small for us to ever see directly, yet shaping everything built upon them. And some physicists have gone further still, proposing that space-time may have more than 4 dimensions, that the 3 dimensions of space and 1 dimension of time we experience every day might be only part of a much larger structure, with additional dimensions curled up so tightly, so small, that they remain completely hidden from ordinary experience and observation. These extra dimensions, if they exist, might help explain some of the deepest mysteries of physics, including, perhaps, some of the very strangeness we find at the heart of black holes themselves. And so, After everything we have explored tonight, the merging galaxies, the rippling gravitational waves, the invisible dark matter, the hidden information stored upon an event horizon, we arrive, gently, at a simple and honest truth. Scientists still don't know what happens at the exact center of a black hole. Deep within, where all of the mass of a collapsed star or of countless merged giants becomes compressed into a single, infinitely dense point that we call a singularity, our current understanding of physics quietly breaks down, unable to describe what truly occurs at such extremes. It is not a failure, but an invitation, a reminder that even after a century of extraordinary discovery, the universe still holds its deepest secrets closely, patiently, waiting for a future understanding we have not yet reached. Let this rest over you now gently, a faint warmth left over from the birth of everything, an invisible universe mostly hidden from view, a speed limit woven into the fabric of existence itself, information held quietly upon the surface of the darkest objects we know, and at the very center of it all, a mystery still unsolved, patient and unhurried, waiting exactly as it has for billions of years. There is nothing here that needs to be understood completely tonight or ever. Some things are simply meant to be held loosely, turned over gently in the quiet corners of the mind, appreciated for their vastness rather than fully grasped. Let your thoughts settle now, soft and unhurried, drifting like that faint ancient light, still traveling gently toward you from the very beginning of time. In the next part of our journey, we will begin to ask, at last, what it might truly mean for these black holes, scattered across billions of galaxies, wrapped in mystery and information and unanswered questions, to somehow reach across the emptiness and connect to one another. For now, simply rest, and let the quiet hum of the universe hold you exactly where you are. Let your body sink once more into stillness, and let your mind drift back into the quiet dark we have been exploring together. We left our thoughts resting on a mystery at the very center of a black hole, a place where our current understanding of physics quietly runs out of answers. Tonight, let us look toward the future of that mystery, and toward the very long, slow future of the universe itself. Black holes may help scientists discover a theory of everything, a single, unified set of equations that could describe every force and every particle in existence, from the vast pull of gravity down to the smallest behavior of subatomic particles. For nearly a century, physicists have searched for a way to unite the two great pillars of modern physics, the smooth, curving geometry of gravity described by Einstein, and the strange, probabilistic rules of quantum mechanics that govern the smallest scales of reality. These two frameworks work beautifully within their own domains, and yet they do not fit neatly together, and nowhere does this tension become more apparent than at the heart of a black hole, where immense gravity compresses matter down to a scale small enough that quantum effects can no longer be ignored. It is here, in this strange meeting point between the very large and the very small, that many physicists believe the answers we are searching for may finally be found. Even as we search for such grand and unifying answers, our understanding of black holes themselves continues to shift and grow. Supermassive black holes may grow faster than we once thought, with recent observations suggesting that some of these giants reached enormous sizes far earlier in the universe's history than earlier models predicted, growing at a pace that challenges our previous assumptions about how quickly matter can spiral inward and accumulate. It is a gentle reminder that even our most careful theories remain works in progress, refined and reshaped as new observations arrive, patiently correcting our understanding of just how quickly these dark giants can come into being. To make sense of all of this complexity, scientists rely on tools far beyond simple observation alone. Computer simulations help scientists study black holes, recreating the swirling motion of gas and dust, the bending of light, the violent final moments of two black holes merging together, all within the careful, controlled environment of a supercomputer. These simulations allow researchers to test their equations against countless imagined scenarios, watching, in effect, digital black holes form, feed, merge, and evolve across millions of simulated years, compressed down into hours or days of computing time, offering glimpses into processes far too vast, too slow, or too violent to ever observe directly and completely from Earth. And our ability to observe these giants directly continues to grow as well. Future space telescopes may reveal thousands more black holes, instruments currently being designed and built with the specific purpose of detecting fainter, more distant, and more varied black holes than we have ever been able to study before. Where we currently know of a relatively small number of black holes in detail, these future instruments may uncover thousands, even tens of thousands, expanding our understanding not just of the extremes, the largest and most active giants, but of the full, quiet diversity of black holes scattered throughout the universe, most of which remain hidden from us today, simply waiting to be found. As our instruments grow more sensitive, we may also begin to detect stranger phenomena still. Black holes can produce echoes in space-time, faint secondary ripples of gravitational waves that some physicists believe might follow the main signal of a black hole merger, subtle reverberations that could hint at the deepest, most mysterious structure of the event horizon itself. These echoes, if they are truly detected and confirmed, would be extraordinarily faint, barely distinguishable from the natural noise of our instruments, and yet they carry within them the tantalizing possibility of learning something entirely new about the true nature of these objects, subtle chimes ringing out long after the main event has already passed. Whatever new discoveries await, one thing remains clear when we consider the very long future ahead. Supermassive black holes can outlive most of the universe's stars, persisting long after the last stars have burned through their fuel and faded quietly into darkness. While even the longest-lived stars will eventually exhaust their nuclear fuel over trillions of years, the black holes they helped feed and grow will remain, patient and largely unchanging, silent monuments long after the light of the stars around them has finally gone out, presiding over galaxies that will have grown dark and quiet, their once brilliant centers reduced to little more than scattered embers. And yet, even black holes are not entirely permanent. Black holes slowly evaporate, an extraordinarily gradual process predicted by the physicist Stephen Hawking, in which black holes emit an almost imperceptibly faint stream of particles over unimaginably long periods of time, slowly losing mass as they do. This radiation, now called Hawking radiation, is so faint for any ordinary black hole that it would take far longer than the current age of the universe to have any noticeable effect at all. A whisper so quiet it would take longer than all of cosmic history so far just to begin to be heard. But across the truly vast stretches of time that lie ahead, stretches so long they make even the current age of the universe seem like a single brief moment, even black holes might eventually disappear, slowly evaporating away entirely, their mass and energy radiated outward in faint whispers of particles until, at last, after a span of time so long it defies ordinary comprehension, nothing remains of them at all. The universe's greatest and most enduring giants, the supermassive black holes that once anchored entire galaxies, would finally, gently fade away. And what would remain after even the black holes have gone? Some physicists believe the universe may experience a heat death, a state in which all energy has spread out so evenly, so completely, that no more meaningful change can occur. No stars, no black holes, no motion beyond the faintest, most uniform thermal noise, spread endlessly across an unimaginably vast and cold expanse of space. It is not an ending marked by any dramatic collapse or explosion, but rather an ending marked by stillness, by balance, by the final settling of everything into perfect, silent equilibrium. This vision of the far future rests upon another quiet, ongoing truth. The universe may continue expanding forever, its galaxies drifting ever further apart, its space stretching ever thinner, carried onward by the same accelerating expansion we spoke of earlier in our journey together. If this expansion continues indefinitely, as much of our current evidence suggests it will, then the universe's story may simply continue, quietly, gently, for a length of time so vast that trillions of years become merely the earliest, briefest chapter in a story with no true final page. Let this settle over you now, softly. A universe stretching endlessly outward, its black holes patiently outliving its stars, only to fade away themselves after spans of time too vast to hold in the mind. And beyond even that, a long, quiet stillness, not an ending exactly, but a kind of vast, patient rest, the universe finally, fully at peace with itself. There is nothing frightening in this vision, only a deep and gentle vastness, the same vastness you might feel gazing up at a truly dark, star-filled sky, aware of how small and brief your own place within it is, and yet comforted, rather than unsettled, by just how much quiet, patient time stretches out ahead. Let your breathing slow further still. Let your thoughts loosen their hold on wakefulness, and rest here, within this long, unhurried future. In the next part of our journey, we will turn, finally, back to the question that began our night together, and ask what it might truly mean for these vast, patient giants to connect not just within their own galaxies, but across the emptiness that spans the whole of the universe. For now, simply rest, and let the slow expansion of the universe carry your thoughts gently outward, into the dark. Let your body settle once more, heavy and warm, sinking into the soft dark. We have traveled far tonight, across billions of galaxies, into the crowded hearts of feeding black holes, through mergers and gravitational waves, out to the very edges of the universe's long future. Now, gently, let us return to the question that carried us into this journey in the first place, and allow ourselves softly to imagine. Wormholes exist only in theory, strange and elegant solutions that emerge from the same equations Einstein used to describe the bending of space and time. On paper, a wormhole is a kind of tunnel, a shortcut connecting two distant points in space, allowing a traveler to pass from one location to another without crossing the vast distance between them directly. The way folding a piece of paper in half might allow a pencil to pass through both layers at once, rather than traveling all the way across the flat page. No wormhole has ever been observed, no evidence has ever confirmed that they truly exist beyond the quiet elegance of mathematics, and many physicists suspect that even if they could exist, they would likely be far too unstable, collapsing in an instant, long before anything could ever pass through. And yet, within the equations themselves, the possibility remains, patient and unconfirmed, a quiet door left slightly ajar. Because of this, some scientists wonder whether black holes could hide wormholes, whether the strange, extreme geometry at the heart of a black hole, the same region where our physics quietly runs out of answers, might somehow connect, in theory, to another black hole somewhere else entirely, forming a bridge across otherwise unreachable distances. This remains deeply speculative, resting more on the edges of theoretical curiosity than on any confirmed physical reality, and most physicists remain quite doubtful that such a connection could ever truly exist, or ever be survivable if it did. But tonight, we are not concerned with certainty. Tonight, we are simply allowed to wonder gently about what such a connection might mean, if it were true. So let us wonder together now, softly, and ask our question fully at last. If black holes connected every galaxy, the cosmic web would become a travel network, an unimaginably vast, invisible lattice linking one galaxy to another, not through the slow crawl of ordinary space, but through hidden passages tucked within the darkest hearts of these giants. The same web of galaxies we described so long ago in our journey tonight, stretching across the universe in filaments and clusters, would become something more, a kind of cosmic map, each black hole a quiet doorway, each connection a thread woven invisibly between galaxies separated by millions or even billions of light years. In such a universe, a black hole network could change the meaning of distance itself. The vast gulfs we spoke of earlier, the millions of years light takes to cross the space between galaxies, might no longer represent an impassable separation, but simply a different kind of distance altogether, one measurable not in light years crossed slowly through ordinary space, but in the number of connections traveled through this hidden network. Two galaxies that appear, from our current vantage point, to be almost unimaginably far apart, might, within such a network, sit only a single quiet step away from one another. And in this imagined universe, a connected universe might feel much smaller, its true vastness hidden behind an intimate, quiet web of shortcuts. The way a sprawling city might feel smaller once you learn its hidden alleyways and shortcuts, paths unknown to those who only ever travel its main streets. The lonely distances we described earlier tonight, the isolating stretch of accelerating expansion slowly carrying galaxies apart, might exist alongside this deeper, hidden closeness, two truths resting quietly together, the vast openness of ordinary space and the intimate closeness of a hidden network running just beneath it. Such a discovery, if it were ever confirmed, would represent something extraordinary. A connected black hole network would completely change the universe, or rather, it would completely change our understanding of it, revealing that the very structures we once thought of as the most destructive, the most isolating, the endpoints of matter and light, were in truth serving as bridges all along, quiet connective tissue running beneath the surface of everything we thought we understood. Within such a network, certain black holes, perhaps those at the heart of especially massive galaxy clusters, might become especially significant. A connected black hole network could create cosmic crossroads, points where many connections converge, hidden hubs linking not just two galaxies, but dozens or hundreds, gathering points within this imagined structure the way a great old city might sit at the crossing of many ancient roads, its importance shaped not by size alone, but by how many paths happen to meet quietly within it. And beneath the vast, glowing structure of galaxies and stars that we can actually observe, a connected black hole network could become the universe's hidden skeleton, an unseen framework running beneath the visible cosmos, the way our own skeletons rest quietly beneath skin and muscle, unseen yet fundamental, shaping the form of everything built upon it. The glowing cosmic web of galaxies we described so long ago tonight would remain the visible surface, while this imagined network of connected black holes would rest just beneath it, quiet, hidden, and foundational. If such a structure were ever truly confirmed to exist, a universe connected by black holes would rewrite cosmic history, transforming our understanding of everything from galaxy formation to the movement of matter across the largest scales, revealing that the story of the universe was never truly a story of isolated islands drifting apart, but a story of quiet, hidden connection all along, present since nearly the very beginning, waiting patiently for us to notice it. And perhaps, in the end, this is the quiet comfort such an idea offers. A galaxy-wide black hole network could preserve cosmic unity, holding every corner of the universe gently linked together even as ordinary space continues to stretch and pull galaxies further apart. Even as the accelerating expansion carries distant galaxies beyond our horizon, even as the universe grows colder and quieter across trillions of years, such a network, if it existed, would mean that nothing was ever truly isolated at all, that beneath every vast, lonely distance, a quiet thread of connection remained. We do not know tonight whether any of this is true. The physics remains uncertain, the evidence remains absent, and most careful scientists would gently caution us against believing too firmly in such an idea. And yet there is something deeply comforting in simply imagining it, in allowing ourselves, just for tonight, to picture a universe where nothing is ever truly alone, where every galaxy, every black hole, every quiet corner of the cosmos remains linked, however invisibly, to everything else. Let this image rest over you now, soft and unhurried. A hidden network of doorways, tucked within the darkest hearts of galaxies. A universe that feels, underneath its vast, lonely distances, quietly, intimately connected. Let your thoughts drift along this imagined web, from one galaxy to the next, weightless and unhurried, needing to travel nowhere at all, simply resting in the gentle possibility of connection. In the final part of our journey together tonight, we will bring these threads gently to a close, returning at last to where we began, beneath a sky full of stars and settling fully into rest. For now, let your breathing slow further still, let your body grow heavier, and drift softly into the dark, held loosely by a universe that may, in ways we cannot yet know, be more connected than it has ever seemed. Let your body sink fully now, heavy and warm, into whatever quiet place is holding you. We have traveled the length of the observable universe tonight and drifted even into the soft, uncertain territory of pure imagination. Let us gather these final threads together gently and bring our long journey to its rest. If such a network of connection truly existed, woven quietly through the hearts of galaxies, it opens the door to an idea larger than distance or gravity alone. A connected universe could create a cosmic civilization, an imagined future in which intelligence spread not just across a single world, or even a single galaxy, but along this hidden lattice itself, moving gently from one galactic home to another, not as strangers crossing an impossible gulf, but as neighbors, linked quietly beneath the surface of the visible sky. It is only imagination, of course, a soft speculation offered for the pleasure of wondering rather than any claim of certainty. But there is something gentle in picturing it. Minds and lives connected across a scale so vast it once seemed entirely beyond reach. And in such an imagined universe, if every galaxy were connected, discovery would never truly end. Each new pathway followed might lead not to an answer, but to another galaxy entirely, another sky full of unfamiliar stars, another quiet mystery waiting patiently to be noticed. Rather than a universe with a final edge, a final page, a final answer, this connected cosmos would simply keep unfolding, one gentle doorway opening onto the next, forever. Every journey through a black hole network would reveal new wonders, each connection carrying a traveler, or perhaps simply a wandering thought, into a completely different corner of the universe, past galaxies never seen from Earth, through clusters and voids and filaments of the cosmic web we described so long ago tonight. Each stop along the way as strange and beautiful as the last, none of them final, none of them the last wonder the universe had to offer. And close to such a black hole, even the sky itself would transform. The night sky would look different near a black hole, its immense gravity bending the light of every star into strange, curved, distorted patterns, some stars appearing to smear into thin arcs of light, others seeming to multiply into faint duplicate images. The whole sky warping gently around the black hole's silent form the way a reflection warps and bends across the surface of still water disturbed by a single falling drop. It would be a sky unlike any we have ever known, beautiful in its strangeness, unfamiliar in every direction. Even without traveling anywhere at all, we continue learning about these giants from right here at home. Astronomers use multiple kinds of light to study black holes, not just the visible light our eyes can detect, but radio waves, X-rays, infrared and ultraviolet light, each revealing a different part of the story: the glowing disk of infalling matter, the powerful jets launched outward, the faint gravitational influence on nearby stars. Together, these different kinds of light form a fuller picture, layered gently over one another like different colors of paint building slowly into a single complete portrait. And this portrait exists within a universe that is, in its own quiet way, endlessly renewing itself. The universe is constantly recycling matter, the same atoms drifting from dying stars into new clouds of gas, from those clouds into newly forming stars, from stars into planets, and sometimes eventually into the slow, patient pull of a black hole. Nothing is ever truly wasted, only transformed, passed gently from one form to another across spans of time too long to fully comprehend. The same quiet cycle by which the calcium in your bones and the iron in your blood once belonged to a star that lived and died long before our sun was born. Yet despite everything we have explored tonight, it is worth remembering that most stars never become black holes at all. Only the most massive stars, those many times larger than our own sun, end their lives with enough gravity to collapse all the way down into a black hole. Most stars, including our own sun, will instead end their lives more gently, swelling briefly, shedding their outer layers softly into space, and settling at last into a small, quiet, slowly cooling ember called a white dwarf, drifting on peacefully rather than collapsing into darkness. And yet, for the black holes that do form, especially the supermassive giants at the hearts of galaxies, their story stretches on far longer than almost anything else in the universe. As we discovered earlier tonight, supermassive black holes can outlive most of the universe's stars, remaining long after the last light of the galaxy around them has quietly faded, patient monuments standing at the center of an increasingly dark and silent cosmos. And after everything, after every fact gathered gently across this long night together, we return to a simple, honest truth. We are only beginning to understand black holes, these strange and beautiful objects that bend light, warp time, store information, launch jets across galaxies, and rest quietly at the hearts of nearly every large galaxy in the universe. Every question we have asked tonight has opened onto another, every answer revealing a little more of how much remains still unknown, still waiting patiently for future minds and future instruments to explore. And perhaps that is the gentlest truth of all to rest upon as you drift now towards sleep. The greatest mystery is that the universe is still full of questions, endlessly, patiently, comfortingly full of things we do not yet know. Not as a source of worry, but as a quiet kind of company, the reassurance that no matter how far our understanding stretches, there will always be more waiting gently beyond it, more wonder, more darkness worth wondering about, more light still traveling toward us from somewhere impossibly far away. Let your body rest now, fully and completely. Let your thoughts loosen entirely from wakefulness, drifting softly the way starlight drifts across the emptiness between galaxies, unhurried, patient, arriving exactly when it is meant to arrive. Somewhere above you, whether you can see it tonight or not, black holes rest quietly at the hearts of countless galaxies, spinning slowly, feeding rarely, connected perhaps by threads we may never fully understand, holding the universe gently together across distances too vast for the mind to hold. You do not need to understand any of it completely tonight. You only need to rest, held loosely by a universe that has been patiently unfolding for nearly 14 billion years, and will continue unfolding long after this quiet night has passed, full of mystery, full of connection, and full always of gentle, unanswered wonder.